Okay, this is going to be the AP Statistics Chapter 13 lesson on experiment design. So let me go ahead and display the screen here. Start with the notes only. Okay, so in Chapter 11, we talked about randomness and how to use randomness to simulate data. We also learned some randomization techniques like the calendar or calculator random integer feature and also the use of a random number table. And then in Chapter 12, we talked about different sampling techniques and then the terminology for different kinds of biases. What we're going to talk about in Chapter 13 is the difference between observational studies and experiments, and how experiments is the only, conducting an experiment is the only way to establish a cause-effect relationship, and we'll try to see why that's true, what makes a good experiment. Basically, if you collect data from the real world and you meet certain criteria, then it's called an experiment, and anything else is called an observational study. So let's first talk about observational studies. In Unit 2, we looked at associations between data variables, right? These data were collected simply by observing situations that were occurring, and there wasn't really any attempt to control what was happening. When we do that, when we don't try to control what's happening, we just observe what's happening, then that's called a study or an observational study. And there are two general categories of them. One's called a retrospective study, and the other's a prospective study. And the difference is that a retrospective study is retro means old, right? So that's about looking at information that has already occurred in the past. So subjects are identified after the events have already occurred, and then the results are studied. So for example, let's say that you decide that you want to determine if there's some sort of association between learning a musical instrument and performance in academics in school. You might look at the information from a high school senior class about how they're doing right now, and then go back and ask them about information in the past, like, did you take music lessons? You know, how much music did you take, and all that kind of stuff, right? So that's about data that's already occurred. You're selecting the subject after the event has happened. So that's called a retrospective study, right? A prospective study would be if the subjects are identified in advance, and then some sort of a survey is conducted once or over some period of time once you've selected the subject. So the subject selection happens prior to the stuff you're observing happening. So maybe we identify a group of young students who state they're going to learn a musical instrument and a group who will not. And then we track those two groups' performance over time and then check in over their entire school. That's called a prospective study because it's still happened. It's still yet to happen, right? And there's a little bit of a reason why we would say that the prospective study is a little bit better, right? This is slightly better. And the reason for that is just because we have a chance to try to come up with our subjects in a non-biased way before we see what's happened. If we wait until after the study has been completed or after the evidence have already occurred, then we might be likely to either drop people or include people in the study based on what happened, right? So if you want really an unbiased result, it's better to select the subjects before and then see what happens rather than go back after the fact, because there's a higher chance of having bias. Okay. So observational studies are fine for revealing associations, strengths of associations. But in Unit 2, we talked about the fact that an association, even if it's strong, does not imply causation, right? We don't know for certain that changing one variable will cause a change in the other because there might be lurking variables or other reasons. Remember how we said if you had the situation where you had the number of TVs in a house and lifespan at death, maybe there's a strong association here. That's true that when people have more TVs in their house, they live longer, right? But what's really happening is something else is going on that's affecting these things, right? In other words, you can't necessarily change the number of TVs and can have that cause a change in lifespan, right? So we said we can't, we can't say, we said it this way: association is not the same as causation, right? Or correlation is not the same as causation, right? Now we're going to say a big unless we conduct an experiment. So the one way that you can show a cause and effect relationship is if you conduct an experiment. So now we're going to see what makes something an experiment and why is it that allows us to say cause and effect. All right, so some terms, first of all. The things that you're experimenting on are either called experimental units or sometimes participants or subjects when they're people, right? A group is just a collection of experimental units where you're doing the same thing with them, right? A factor is some explanatory variable that we're controlling the levels for, right? And then a treatment is when we're actually applying different levels of that factor to some group. And then what we're watching, what we're observing as the output to see what the result is, the thing we watch is called the response variable. That's the variable that we're measuring to see if there's an effect from the treatment. All right, so we're going to take a specific example here. This is completely made up, and normally when we do this in person, we do this with this bags of tokens and stuff. But again, I've created a program online that will allow us to do this activity virtually. So you'll be able to do it from your home here, but I'm going to have to show you how the results from the whole class look, so we can learn something from it. So here's the scenario we're investigating. Again, this is all made up. Let's say we're working for a company that's created, or maybe we're doing statistical analysis for a company, to evaluate a new drug that's supposed to improve the general health of all people who use it. They use this drug over a 6-month period, and it's expected to result in a significant increase on a health survey that we give them, whose score determines how healthy they are at that time. Right, so a higher score means that they're more healthy. So we have to decide how we're going to conduct the experiment. We have a lot of leeway in how to do that. So let's say that we feel that we can get by with doing this just with 60 people. Okay, so we're going to test this drug on 60 people. This is a very early trial. Of course, drugs are tested on thousands of people in the later stage of investigation. So what's the factor that we're investigating? Well, the factor is the drug. There's a single factor here called the drug. And that's what we're trying to see if it makes a difference. So in order to see if the drug makes a difference, we have to have at least 2 different levels of this factor that's being used in the experiment. In this case, we're just going to give the drug to some people, and we're going to not give the drug to other people, and we're going to see if there's a difference in that groups of people. Okay, so the groups, well, we're going to have 2 groups because we have 2 different treatments here. Right? One treatment is going to be that they take the drug for 6 months, and the other treatment is that they don't take the drug. And so that means we need one group of people to take the drug and one group of people to not take the drug. So there's a group for every treatment. Okay, and since we want 60 people to experiment on, that means we're going to divide them into 2 groups of 30 people. 30 people are going to take the drug and 30 people are not going to take the drug. And then the response variable that we're going to measure is at the end of the time, we're going to give them this health survey. And then we'll look at their score. And then what we can do is we can take all of group 1 and find the average health score for group 1. And we can take the average health score for group 2, and we can compare those 2 averages. Right? The idea would be is if the drug mattered, then this average should be higher. Right? That's what we're thinking. We're hoping this is going to be higher than this average because the drug made a difference. All right. So that's the idea. And to start with, so we already have the drug available, but we need to find some subjects. Okay, so it turns out that fairly near our offices, there's a library that has a park right next to it. So both of those are good places to ask people to participate. So we set up a table, we ask people to volunteer. Maybe we give them an incentive and we tell them they're participating in this, and it's a general drug that's we know is safe. We're trying to determine if it's effective. And just for participating, when we're done with the study, we'll give them a 10-year supply of the drug for free if we find that it is effective, just to get people to sign up. So we set up a table at the park and a table at the library, and we just sign up 30 people at each location. It happens to be 30 people. All right. And so to keep it simple, let's just use the people we signed up as at the park as group 1, who's going to receive the drug. And we'll just take all the people that we signed up at the library as group 2, who will not take the drug. And so we can draw what's called an experiment design diagram here to show what we're doing. So we've got these 30 people from the park that we're going to call group 1 now. We've got these 30 people from the library that we're going to call group 2. And then we're going to have group 1 take the drug for 6 months. Group 2 is not going to take the drug. And then at the end, we're going to find the mean of the group 1 group people, the mean of their health scores on the health survey, and the mean of group 2. And we're going to compare those 2 to see if this mean is higher. All right, so that's the structure. All right, so like I said, usually we would use tokens, but I'm going to switch away here to showing the whole screen because I want to show you how we can do this together. And you can do this with me at home. It's based on running something on my website. So let me share the entire screen. And we're going to browse. So I'd have you open a browser window and go to my website, mrfelling.com, but then /experiment. So if you go to mrfelling.com/experiment, you'll see this page right here that looks like this. And I'm going to read it. It says the Park Library Experiment Activity. We've collected samples of 30 people from the library and 30 people from the park for our experiment. Okay, to keep it simple, we're using the sample from the park as group 1 who receives the drug, and the sample from the library as group 2 who gets no drug, and then we compare the mean health scores. So to conduct the experiment, we give the drug to group 1 and nothing to group 2. We monitor through a 6-month cold and flu season. And then in the spring, we give a survey to each student to measure the health, right? Higher numbers equal better health, okay? And so here's the results. Okay, and if you run this, you're going to get slightly different results, right? So this is simulating something real, all right? And so each of these numbers is the score on a health survey. So what we're going to do is just compute the average health score for the group that in group 1 who took the drug, and then the average health score for group 2 that did not take the drug. So you would grab a calculator and you would enter, maybe clear the lists, and then enter in to list 1. We're going to enter all the group 1 scores, and we'll enter the group 2 scores into list 2. So we can, I'll do that. You can do that as well. Okay, 60 numbers to enter, so it'll take a little while. Okay, so I've got my data entered, list 1 and list 2, and it'd be fast for me to go ahead and compute the mean. I'll just use one variable stats. So if we go stat, and then over to calculate, and then one variable stats, and I run it on list 1 with no frequency list, I'll get that the mean for the group 1 turned out to be 35.4. And then if I run, so I'll suggest that you write that down on a piece of paper. And then we'll go back and we'll run one variable stats again, but this time on list 2 for the group 2 people. And theirs was 24.6. Right, so the drug seemed to improve health scores. That's the question. Do we think the drug seemed to improve health scores? So let me go back to the notes for a second. And what I got was, I got that the mean for the people who took the drug was 35.4 on their health surveys and was 24.6, which seems like a pretty big change, right? These numbers are in the 20s and 30s, and this difference is over 10. So maybe I could define something called the improvement. The improvement would be the number for the drug minus the number for no drug, right, which turns out to be 10.8. So basically an improvement of almost 11. Let's just round everything to the nearest decimal. 11 points on the health survey from taking the drug. Wow, seems like it's really great. And, you know, if you did this correctly, you should actually have gotten these exact same numbers, because the way I program this is it's the same group of people for everybody that runs this online. It's going to look a little different because they get randomly selected, but it's still all the park people and all the library people. So actually everybody should have got the same exact number. And when we do this in class, everybody gets this, and we end up concluding the drug would really work, right? But here's the problem. Other research groups are also investigating this drug, and they found that there was no significant difference in the means, right? So they concluded the drug was ineffective, and in fact, it does turn out that the drug is completely ineffective. Even though we saw a big difference, the drug actually is worthless. So what happened? Why did our experiment come to the wrong conclusion? Okay, so here's the problem. It turns out that we have potentially uncontrolled factors between the people other than whether they took the drug or not, right? We want there to be only one difference between group 1 and group 2, which is that they took the drug, because I want to be able to say this difference that we saw is due to the drug. The problem is if I go back to, let me actually go back to the screen here. So on your internet thing here with the experiment, if you press the part 2 button now, you can read through here. Actually, let me go back to the notes. The problem is that there are other things that are different between the people besides the drug, right? So um, I'll go back to this picture. We want this to be that the drug is causing this difference. The problem is these are just 30 people that we got, and these are 30 people. There are other things that might be different between these groups, right? Like maybe the ages of the people matter. Maybe their general health, right? Other things. Do they exercise? Other things like that. That might be different, that are really the reason why these are different besides the drug, right? We have the drug, right? But then we have other differences between the people that also might be contributing to this difference that we're seeing here, right? So the good news is that's actually very easy to fix. All we have to do is, instead of just taking the park people and making them group 1 and the library people and making them group 2, we just lump all 60 people together, and then we randomly assign the people using a random process into group 1 and group 2. Okay, then if we see a difference, any of these other differences back here, like age or exercising or anything else, right, those things will tend to be split between the two groups, right? So if you press the part 2 button on your result, on your online experiment thing, it takes you to another screen where we're going to redo the experiment, but this time we're going to set it up by taking the 60 people we got from the park and the library, group them together into one group, but then randomly assigning them 30 to group 1 and 30 to group 2, where group 1 gets the drug and group 2 doesn't get the drug. And so we run that again, we run the experiment again, and we have a different set of numbers. So go ahead and type in your numbers in the calculator, and I'll do the same. We're going to have to clear our lists again, and then enter this again. So I'll put group 1 health scores here, so, and then the second list for the group 2. Okay, so we got that in there, and we will run the averages again. So I'll do stat calculations on list 1 to get the list 1 mean. And so this time I happen to get 31.3. So let me go back to my notes here for a second and say this time I got mean as 31.3 for group 1. And when I run the statistics on list 2 from group 2, I get 27.5. 27.5. So if I look at the improvement, and you can do this as well, look at the improvement, it would be 31.3 to 27.5. 31.3 to 27.5 is 3.8. Okay, remember how before we said that the drug improved 11? Now it's down to only 4, at least for mine, and you probably got something different, right? So what we do typically then is we say, okay, now we didn't all get the same improvement, and I ask everybody to type in the chat or to call out their, what their improvement numbers were, and let me show you what a typical dot plot is for a class. So if you look at the improvement, it's going to end up being, let's see, I have like quite a few people who had no improvement. I had, let's see, this is a typical run from a small class. Had some 4s, some 5s, and I even had one person who had a decrease of 7. And then I had 2 2s, I had a 3, a 4, a 5, and I had 1 6 and 1 positive 7. So yeah, it looked like the variation was all over the place. And this makes sense because now we're randomly assigning between the groups, right? But so the drug would be effective somewhere out here. Maybe the question is the change big enough to be significant? A change of 1, probably not. But maybe out here, we would say a change of 5 or more. Maybe you can say that's significant, right? So this means the drug worked. But anything over here, I don't know. Basically, drugs doesn't seem to have an effect, or maybe even worsened in some cases. This just looks to me like the drug, like there's some random differences between people on their health scores, and the drug isn't really doing anything. So now that we randomly assigned, we can see the drug worked really in a very small percentage of the cases. So it does not seem like the drug was effective. Here's the problem. In the first experiment, right? Yes, we had the drug, right? But there's all these other sorts of things going on here. Age, general health level, and a biggie, do they exercise or not? Okay. And if we don't randomize between the people, all those differences are still differences in group 1 and group 2, right? So we have no idea whether or not the differences that we saw between the means is due to the drug or due to these other factors. Okay, so we would say that these variables or factors like drug and exercise or age or health are all what we call confounded. We can't separate their effects out on the response variable. Okay, so in the second experiment, we did a random assignment here, and that meant that the only thing that was really different between the groups was drug. And the reason for that is because all those other factors, if we have some things that matter, they're going to be some people randomly are going to be put in group 1 and some in group 2. And so when we look at the differences between the group, those differences will be subtracted out. Okay, so it turns out that there is one thing that is really important for the health score. So let's go back to the online experiment. And if you click on the part 3 button down here, it will summarize why did the first experiment come to the wrong conclusion. It's because of uncontrolled factors. And in fact, it turns out there is one really important uncontrolled factor: how much the people exercise. And so if we go back and ask each person in the survey if they exercise, we can divide the people into 2 classifications: the exercisers and the non-exercisers. And so this was what I got on my first group, right? But what I've done is the programming codes all the exercisers as green and the non-exercisers in red. And if you look at the people we got from the park versus the people we got from the library group, the park group just happened to have a lot more people who exercise, which kind of makes sense. They might be exercising at the park, right? And the library group, on average, had more people who didn't exercise. Doesn't mean that you couldn't exercise, right? But there were 22 exercisers and non-exercisers in the park group, but only 8 exercisers and 22 non-exercisers in the library group. And it turns out that's really why the group 1's health scores were higher, because a lot of those people exercised. Okay, when we did the second group, this was my group, and because these were randomly assigned, that means roughly half the people should be of the exercisers should be in group 1 and half in group 2, and half the non-exercisers should be in each group. And sure enough, when I did this random assignment, I got 16 exercisers in my group 1 and 14 exercisers in my group 2, right? And you probably had similar results as well. And so yeah, there's a lot that tended to even out. That's why we saw some. Now, when we're looking at this difference here, these differences here, this difference is just about how well that averaging is working, right? Sometimes we happen to get a higher number of exercisers in the group that's group 1, and so we got the scores that were in this range. And sometimes we happen to have it so that there were more non-exercisers in group 1, and that's how we got these numbers. But when you have things that are kind of centered at 0 here, it's a pretty good indication that there's some other randomness going on from random sampling variation, and it's not due to the drug, right? The drug is really not affecting things. All right, so that's the key there. Let me switch back to showing just the notes, and then I want to wrap up some more stuff about terminology. Right. So unless we do randomization, there's un there's other confounded variables that could be different between the subjects that we're not subtracting out. And effectively, by randomizing, we're subtracting out the effects because you get an even number in each one. The good news is not only does this remove the effect of exercise, randomization here removes, it controls for all differences between people, including things we're not even aware of. There might be things we're not aware of, kind of like in the soup, right? Are you aware that somebody put peas in the soup? Well, maybe we're not aware of some difference between the people, and this will still average that out. Okay, so one question is, how big of a difference would you have to have in the response variable before you'd say that the drug was significant? So the whole point is to observe a change, right? We're not going to be able to answer this completely till we get through probability and into second semester. But for now, we're going to say we have convincing evidence if or the result is statistically significant if the observed differences just seems too large for us to believe it happened just due to the natural variation or by chance, right? If you were to do like a box and whisker plot of the health scores of the control group people and the people who got the drug, and this was the difference in the means, and that difference is kind of within the normal variation of people from person to person anyway, we'd probably say that's not very significant, right? On the other hand, if we had, like a pretty tight grouping here of like most of the people scored between there and there or there and there, and then there was this much difference, well, that difference now looks pretty large in comparison to the difference here. So we would maybe say, well, maybe that difference is statistically significant. So kind of a hand-wavy answer to that, but second semester we'll be able to answer that very precisely, whether or not that difference is big enough to consider statistically significant. All right, so what makes a good designed experiment? Only a well-designed experiment can conclude the cause and effect because we're trying to control for everything except for the factor or factors we're controlling. So for a study to be called an experiment, technically it only has to have one thing. You have to have researchers applying a treatment that's different for the groups. That's the one thing that's absolutely required. Okay, but a well-designed experiment that's going to really show something takes further measures to reduce not only bias but also variability. Okay, so let's talk about that. Let's say we have a population that we're trying to investigate. And so we take our 30 people from the park, right? The first thing is we wouldn't want to use a good sampling technique, right? The sampling technique should be an SRS or cluster or stratified sample, something where this sample is non-biased, okay? Because if you do whatever you do after that, if you have a biased sample, there's nothing you can do in your experiment or analysis to compensate for that. So you have to take, using chapter 12 techniques, a good non-biased sample, right? But then once you do that, there's some things you can do in the experiment design to be able to establish cause and effect. To reduce the variability, in addition to just applying a treatment, you want to include random assignments of subjects to the groups. And we can see from our activity today why that's so critical, because that will control for or remove the variation of the differences between the subjects that we know about and don't know about that are not under control, right? By the way, if one group receives no treatment, it's sometimes called a control group, but that's actually not required. You don't have to have a group that receives no treatment. You just have to have at least two groups that receive different treatments. And it could be that they're both getting a treatment. Like, for example, we could have decided to give group one a half dosage of the drug and group two the full dosage of the drug and have no one receive no drug at all. If we do happen to pick that one of the treatments is no treatment at all, then that group has the special name control group. That's not required. But what is required for a good experiment is random assignment of the subjects to the groups. And then you must be controlling at least one factor. That means you are imposing a treatment that's different on the subjects. In this case, it's giving of the drug and withholding the drug. And then the third thing we need for a good experiment is something called replication. And there's actually two different meanings of this, but they're both important. Okay, so one of them is replication of treatment. The randomization is how we control for subjects, but you have to have enough subjects in the group for the averaging to work. So going back to this picture, we had 30 people in each group. That was a pretty decent sized number. Let's say that we had only 2 people in each group. If we had 2 people, that's not really a big enough number so that this averaging of getting some exercisers here and some exercisers here to happen, right? So we don't want to have small groups here. This 30 is allowing us to do what's called replication of the treatment, okay? Because that same treatment is being replicated on a large number of people. That way the averaging effect we just saw can occur. So that's the first reason. And this is AP's understanding of what the word replication means. It's this. If you take like an AP psychology class or other sorts of classes that talk about studies, they usually use the word replication differently to mean the entire experiment must be replicated, okay? In other words, you want to have, your group does the experiment, but then an entire other research group with its own set of subjects and stuff replicates the whole thing from start to finish just to verify your results. That's actually important too. And the reason for that is because of this, right? We saw that when we do an experiment, anything can happen. There's still going to be some natural variation. So if you have 4 different groups that all do the experiment and they all kind of come out in the same, maybe 6 groups do it, 4 of them have this result and 2 of them have kind of unusual results out here, that replication of experiment over and over and over again, right, really solidifies our belief that this result is valid, right? So because anything can happen, you can get the really weird experiment that got -7 or +7. It's good to replicate the whole thing just to make sure that the results you saw are repeatable. That's called replication of experiment. Okay, so 2 meanings of the word replication. Replication of treatment is because the subject groups are big enough that you can have the averaging effect happen. Replication of experiment is repeating the whole experiment. Both of those all these factors are good. So technically, something's called an experiment if you have treatment applied to groups, but it's only called a well-designed experiment when it includes these other things as well. All right. So what if we do know differences in the subjects? Like maybe we've anticipated the fact that exercisers are going to matter, right? That matters, right? So if we want to do that, basically what we can do is we can take the people and divide based on something in the subjects, like whether they exercise or not. And when you do that, you get 2 complete separate experiments that are run in parallel. These are called blocks when we do this. And then when we do this, it's called a block design experiment. So basically you block on something, like say block on exercise, which means first you divide up the subjects based on whether they exercise or not. And then you run completely separate experiments on the exercisers and the non-exercisers. So you replicate the entire design diagram here, right? Now you'd have 30 people here that were exercisers, so you'd only have 15 in each group, right? And same thing here, these 30 non-exercisers, you'd have 15 in each group, but you'd give some the drug, some not the drug. And then when you do the comparison, you do the comparison within each block, okay? The idea is that you're reducing the amount of variation because you're reducing one of the sources of variation in the subjects, okay? All right, so blocking is kind of the same idea for experiments as stratifying is for sampling. If we know there's differences in the subjects and you want to make sure and include some of all of those into the sample, you do stratified random sampling. But in the context of experiments, if you think that the different groups in your sample might behave differently, you can separate them into separate blocks and run separate experiments on each block, right? Blocking and stratifying are done to handle known differences in the subjects. Randomization is done to handle the unknown differences in the subjects and even them out, right? And then blocking also has the effect of reducing the natural sampling variation because you're removing factors in the subjects, right? To see how that works, take a look at this complicated slide. Let's say we did no blocking here, right? And we had some factor here, like the exercising and non-exercising people. So I've got people here written with an orange dot if they don't exercise and green dot if they do, right? So if you have the group of people that were from the park, right, or this was maybe the library group, I don't know which group it was, but if you have one group that had maybe more exercisers than the others, right, maybe you would see some difference here. Here's the means, and you see a difference in the means, right? But if I just have this whole big group, that difference in means is being compared to this wide span of variation, right? So it's hard to tell if this difference is statistically significant because I have all of the variation in the people all in one big blob here. But if you instead block and separate the exercisers from the non-exercisers, if you look at the exercisers and you conduct their experiment, right, you might get that same difference, but this time it's only being compared to the variation between people who exercise, which is smaller than this variation up here. So you're more likely to be able to say that that difference is statistically significant against the smaller variation than against the bigger non-blocked variation. Same thing here. If we have means in these two groups, drug versus non-group, but we have a smaller amount of variation here, it's easier to see this difference as statistically significant. Right? So the real reason we do blocking is to try to reduce the variability in the results, which makes it easier to see small differences as significant. Okay, so a little bit about these experiment diagrams. Sometimes we have to draw these things, and I want to point out some stuff about how you draw these diagrams. So there's two distinct halves in the diagram, right? If you draw a line here between the groups and the treatments, right, the first half of the diagram is all about how the subjects are assigned to the groups. So you have groups, maybe you have blocking into blocks, then you have random assignment at some point into groups, right? That's all on the left side of the diagram here, right? On the right side of the diagram, that has all to do with the treatments and the results. So we specify the treatments for each of the groups, and then we compare the results, right? And there's not really a dashed line here, but I want you to think of there being a wall. Everything for grouping has to do on this side, everything with treatment and results on this side. That means the groups are always shown separate from the treatments like this, okay? All right. You can control more than one factor. You don't have to just give a drug or no drug, right? Let's say that we had two drugs, drug A, which comes in two dosages, 10 milligrams and 20 milligrams, and then we had a second drug, drug B, that comes in one dosage, 50 milligrams. So maybe we have drug A and we want to try not giving it at all, 10 milligrams or 20 milligrams, which is 3 levels of that factor. Then we have a second factor, which is drug B, that we're going to either not give or give at full strength. So there's 2 levels. And so the way we conduct that is we take every combination of all of the levels of all of the factors. So in this case, we have this factor, drug B, which has 2 levels, and we have this factor, drug A, which has 3. So there's going to be 2 times 3, there's going to be 6 different treatments required, right? We're going to have a group that gives neither of the drug. Group 2 maybe will get 10 milligrams drug A but not drug B. Group 3 will give 20 milligrams drug A but not drug B. And then groups 4, 5, and 6 will be the same drug A except with full strength drug B. Right? So when we do this, this is called a randomized 2-factor experiment, right? And its design diagram would look like this. You'd have maybe 60 people. If we have 6 treatments, no drug A, no drug B, 10 milligrams drug A, no drug B, and so on, all these treatments, then you have to have a group for each treatment. So you'd have to have 6 groups. Since we have 60 people to choose from, we're going to randomly assign 10 of them into each of the 6 groups. And then we'll do the treatment on this half of the diagram, and then we'll compare all in one thing within one block. You do all the comparisons all at once. We'll be comparing these means. This is called a completely randomized 2-factor experiment because the 2 factors are drug A and drug B, right? All other factors are being eliminated by this random assignment, okay? All right. There's some other things we can do to make experiments even stronger. One of them is using placebos to accomplish what's called blinding. So humans are notoriously susceptible to errors in judgment, right? We know that when a treatment was assigned, right, it's difficult not to let that knowledge influence our assessment of the response, even subconsciously. So if subjects, the humans, if they're human, and also if the researchers, they're both subject to potentially being biased in this way. So for example, let's say that you're taste testing various colas, but the brands aren't hidden. So brand loyalty biases the results. Or, maybe a particular researcher likes a particular brand of cola. So when he or she presents that cola to the subject to taste test, their body language conveys something about the cola, right? So we can do things that will eliminate this. So let me show you, for example, if we just had a table, right, and we had cups on here, right? But they were labeled Pepsi and Coke and RC Cola. And then we had research back here and subjects out here that were taste testing, right? That would not be a very good thing, right? Because the subjects over here, right, they would be able to, maybe they already think they like Pepsi the best, so they're going to taste the Pepsi and go, yep, I like Pepsi, right? So that would be there's no blinding in this experiment, right? Now let's do what's called single blinding. Okay, single blinding would be, imagine if you had, here's my table with colas on here, right? But I'm not going to allow the subject to know. So the subject doesn't know. So we're just going to label the cups A, B, and C, right? But the researcher knows, right? So the researcher knows that A is Pepsi and B is Coke and C is RC Cola, right? But the subject does not know which is which, right? So this would be blinding the subjects, right? Because the subject can't, if they have any biases, they can't apply that bias. They have no idea which one's which. Unfortunately, that still leaves the researcher, right? The researcher might like have stock in Coke, and so when she presents the B cup, she like somehow, has a smile on her face or something, and she's frowning when she presents the A and the C cups, and that subconsciously affects the subject, right? So that's single blinding. Okay, double blinding, which is really the best. That's when both the researcher and the subject has no idea what's going on. So in this case, you would have your cups here, your A, B, and C, right? And you'd have your researcher here, and you'd have your subject out here, right? Right, but neither of them can know which thing is in which cup. Now, of course, somebody has to know, so you have to employ a third party. There has to be like an organization that knows that cup A contains Pepsi, and cup B contains Coke, and cup C contains RC, and they tell the researchers after the experiment is done. Right? So when the experiment's done, then they tell them, okay, cup B was the Coke, cup A was the Pepsi. And that means while the experiment's going on, right, both these people are blinded. So this is what's called double blind, right? The subjects and the researchers are unaware of that, right? I should probably use the same notation. This is the person who's blind here, right? In this case, no one's blind, subject is blind, subject and researcher are blind. Okay, and then there's occasions when we have to employ something called a placebo in order to accomplish this blinding, because basically blinding means that you're not, a subject or a researcher is not aware of which subject is getting which treatment. Okay, so let's say that humans might have some subconscious reason or maybe even conscious reason to want an experiment to have a particular result. So if they can detect that they're in the group that's the control group or the group that's getting the treatment, that could bias the results. Let's say, for example, that you're talking about some sort of a medicine that's injected with a syringe, right? So if one group gets an injection and the other group doesn't get the injection, right, that means that the subjects know whether they're getting the drug or not, and that could affect something, right? Like especially if it's something like a pain study that's sort of subjective and they have to report on their pain level, right? So the subject will typically be given a fake treatment, right, that replicates the experience of receiving the treatment without getting the active ingredient. So that fake treatment is called a placebo. In this case, it might be an injection, but an injection of just purified water, something like that. All right, in the Park Library drug experiment, the no drug group could have been given a pill that just had nothing in it, no drug. Okay, in fact, it's not unusual for subjects that are treated with a placebo to still show a result just due to their brain kind of wanting there to be a change, right? Actually, frequently 20% or more of subjects in medical studies report that the treatment that they got, even when it was a placebo, was effective, especially when it's things that are where the subject has to rate their symptoms, like a reduction in pain, range of motion, greater alertness, things like that. Often those kinds of studies are affected by people's subconscious belief that the treatment will work. So that is actually referred to as the placebo effect, that even a placebo can cause an effect. All right. And then, okay, so what other improvements could we make in our drug health score experiment besides just blocking on exercise? Well, we could have given the no drug subjects a placebo, right? Given them a fake pill, okay? If there was any sort of bias in the sample, right? We just took our sample at a single park and library. That's a convenient sample, and that means that that may not be very representative. So we might want to do something like randomly call households, from throughout an entire city that's representative of cities in the United States, and do a much better job of getting a really good non-biased sample of people to use as subjects. And then one thing that you might think is, why am I only given this test once, right? People have another factor that we're removing with randomization, but it's still present in the output, is that we have just general health, right? There's differences in general health. So what if we were to first have the people take a pre-survey and then take the survey over again, and then we could take post minus pre to find the improvement for every individual person. So that way, if one person scored a 5 on the survey, but then they went up to 8, but another person scored a 35 and went up to a 38, we would be able to see that the drug had a 3-point improvement in both of those, right? So that's called a match pairs experiment, which we'll talk about that more in second semester. But there are other things we could do to strengthen this experiment beyond what we're seeing. And hopefully what you're getting the impression of, which is true, is it's quite difficult to conduct an experiment that's really strong. And there's a lot of choices to make as a researcher, right? Okay, last little bit on terminology. I know this video is getting really long, but gotta cover it somewhere. We've defined lurking variable as a variable that is controlling other variables, like say wealth might control the number of TVs and the life expectancy, right? The word confounding is when you have something where you're measuring something and 2 different variables are both affecting it, like drug and exercise. Those, we would say that the drug and exercise variables are confounded, so you should know that word, okay? Lurking variable, we should probably avoid that one on the AP exam. It's not official, but confounding is an official term, so you should definitely know how to use that. The word association and relationship, we know that that's the general term. They do use that on the AP exam. It's appropriate to use for both observational studies and experiments, right? We saw this back with categorical versus categorical, like whether people survived and their class on the Titanic, is there an association? You can talk about relationship and association. We talked about this in Unit 2 with like height and the number of steps people took. Is there a slope here? Is there an association between numerical variables? What we did in our drug experiment here is a numerical variable versus categorical, right? So we're measuring health outcome, which is numerical, but then we have for 2 categories, people who took the drug and people who took no drug, right? So we're seeing an association between those. So you can use that with any combination of categorical or numerical variables, right? The word association or relationship. Correlation is the correlation coefficient R. That's only for 2 numerical variables, right? So that's specific, okay? However, the data could be collected either as an experiment or an observational study. It doesn't matter, because we're just analyzing if there's an association. If it comes from an observational study, we can't imply cause and effect. We can imply cause and effect if it's an experiment that collected the data. So causation, also called cause and effect, that's appropriate only for well-designed experiments, okay? We have to have control of a factor and some way to be convinced that there's no other factors interfering with this factor, right? Then we can say the drug causes health scores to increase. All right. And then experimental use units, this can be tricky too. Often questions will ask you to identify what the experimental units are, which can be tricky. So I wanted to show, as the last bit here, 2 examples from actual AP exams. This says biologist is interested in studying the effect of growth enhancing nutrients and different salinity or salt levels in water on the growth of shrimps. The biologist has ordered a large shipment of young tiger shrimps from a supply house for use in the study. The experiment is to be conducted in a laboratory where 10 tiger shrimps are placed randomly into each of 12 similar tanks in a controlled environment. The biologist is planning to use 3 different growth enhancing nutrients and test 2 different salinity levels, right? So we have 2 factors here, right? The first question on the AP test this year was, the length of each shrimp will be measured before and after exposure to the nutrient and salinity environment. Growth for each shrimp is computed from subtracting the lengths. The growth is the length after the experiment minus before. Identify the treatments, the experimental units, and the response variable for the experiment. So the correct answer that year was that the treatments were the tank environments, which contain combinations of the nutrients and salinity levels, right? So you had to have, there was 3 different nutrients, and there was 2 different salinity levels. So there's a total of 6 different treatments. And so they prepared 6 different tanks. Actually, there were a total of 12 tanks. So that meant that 2 tanks were given each of these 6 treatments. So 2 tanks were given A with low, 2 tanks were given A with high, and so on, right? So the treatments are the tank environments. The experimental units in this case are the individual shrimp. And the reason is because we're measuring growth for the shrimp, right? But the response variable is the growth of each individual shrimp, okay? And then they said, but what if we decided to specify this way? The mean length of the shrimp in each tank will be measured before and after exposure. So instead of measuring the individual shrimp, they decided to take the lengths before, the lengths after minus the length before, but take the mean of the after lengths and the mean of the before lengths. So they're subtracting a mean, they're taking the after mean minus the before mean. Right now, identify what the treatment's experimental units were. So the treatments were still the same, the tank environment combinations of nutrients and salinity levels, right? But now the experimental units are no longer the shrimp. Now the experimental units are the tanks that contain the shrimp, because each tank is generating a number, right? It's the mean of the entire tank, right? So it can be very tricky. So for something to be considered an experimental unit, it has to be something which is getting a unique copy of the treatment, and it also has to be producing a number that's used in the response, okay? So very tricky. All right, we'll talk more about that, especially in second semester when we get to reviewing for the AP test, but I'll conclude this extremely long video now. So thank you for watching to the end if you have watched to the end.